When we observe a distant world, the first mistake we tend to make is subtle but fundamental. We assume that recognition implies understanding. A coastline curves in a way we have seen before. Branching patterns resemble rivers. Diffuse layers suggest clouds. And almost immediately the mind compresses these observations into a conclusion that feels efficient, but is in fact incomplete. So the question we must begin with is not whether Titan looks like Earth, but rather, how can two systems governed by the same physical laws produce outcomes that diverge so dramatically? Titan does not confront us with obvious hostility. It does not resemble an environment that instantly signals danger. Through extremes like crushing pressure or intense radiation, instead it presents something more disciplined, and therefore more deceptive. A set of structures that align closely with terrestrial expectations. But in physics, resemblance at the level of shape is not sufficient, because what determines behavior is not appearance, but the underlying variables: temperature, composition, gravitational acceleration, and the way these variables enter into otherwise universal equations. Therefore, from the beginning, we must separate two ideas that are often conflated: structure and substance. Let us establish the first constraint precisely. Titan orbits Saturn at a distance where solar radiation is significantly reduced. The intensity of light, and therefore energy, decreases with the square of distance from the source, which means that by the time sunlight reaches Titan, it carries only a small fraction of the energy available at Earth orbit. This is not a qualitative statement, but a quantitative one. Reduce incoming energy, and you reduce equilibrium temperature. On Titan, this stabilizes near 94 Kelvin, a regime in which molecular motion is drastically reduced compared to Earth conditions. And once molecular motion changes, phase behavior changes, reaction rates change, and entire classes of chemical processes reorganize themselves accordingly. Historically, Titan resisted direct interpretation because its atmosphere is optically thick. Visible light cannot penetrate it effectively, which means early observations provided only integrated signals, rather than resolved surface features. This is not merely a technical limitation. It is a reminder that data acquisition constrains theory. Without spatial resolution, we cannot map processes. Without mapping, we cannot infer dynamics. The Cassini-Huygens mission altered this situation by introducing radar imaging and in situ measurement, effectively transforming Titan from an unresolved object into a system that could be interrogated layer by layer. During the descent of the Huygens probe, the first significant observation was not the surface, but the atmosphere itself. Composition analysis indicated a dominance of nitrogen, approximately 95%. At first glance, this suggests familiarity, since Earth's atmosphere is also nitrogen-rich. However, the remaining fraction introduces the crucial difference. Methane and other hydrocarbons are present in sufficient quantities to participate actively in atmospheric chemistry. Under ultraviolet radiation, these molecules undergo reactions that produce complex organic aerosols, forming a persistent haze. This haze is not passive. It scatters incoming light, redistributes energy, and establishes a vertical structure that affects temperature gradients throughout the atmosphere. At this stage, it is essential to articulate a principle that will recur throughout our analysis. The governing equations remain invariant, but the solutions depend on parameters. For example, the relationship between pressure, density, and temperature in a gas does not change from Earth to Titan. If we compress a gas, pressure increases. If we reduce temperature, average molecular motion decreases. These statements are universal. However, if the temperature is low enough, and the composition is different, the resulting state of the system may fall into a regime that has no direct analog on Earth. Therefore, saying Titan has an atmosphere like Earth is imprecise. A more accurate statement is, Titan atmosphere obeys the same physical laws as Earth atmosphere, but operates in a different region of parameter space. As the probe continued its descent, it encountered measurable wind velocities. This observation is not incidental. Wind implies gradients, differences in pressure and temperature that drive motion. And once gradients exist, transport processes follow. Energy is redistributed, mass is moved, and the system becomes dynamic rather than static. This leads us to the next level of structure, the existence of a cycle. On Earth, we are familiar with a cycle in which a liquid evaporates, rises, condenses into clouds, and returns as precipitation. The important point here is not the identity of the liquid, but the thermodynamic framework that allows such a cycle to occur. On Titan, an analogous cycle exists, but with methane replacing water. Methane can exist as a gas, condense into liquid, and participate in phase transitions under Titan temperature and pressure conditions. If we describe only the sequence, evaporation, condensation, precipitation, we might conclude that Titan possesses a hydrological cycle. However, that terminology carries an implicit assumption about substance. To maintain precision, we should instead say, Titan exhibits a closed phase transition cycle governed by methane. This is where intuitive reasoning begins to fail. The mind tends to associate rivers with water, clouds with water vapor, and rain with water droplets. But in physics, these associations are contingent, not necessary. A river is a flow of liquid under gravity, constrained by channel geometry, and resisted by viscosity. Change the liquid, and you change the coefficients in the governing equations, but not the form of the equations themselves. Therefore, it is entirely consistent for a world to exhibit river-like structures without containing any water at all. We now introduce another parameter that modifies behavior in a systematic way. Gravitational acceleration. Titan surface gravity is approximately 1.35 meters per second squared, which is about 1/7 of Earth gravity. The force acting on an object is proportional to this acceleration. So reducing gravity reduces the downward force experienced by particles and droplets. However, motion is not determined by force alone. It is also influenced by resistance from the surrounding medium. Titan atmosphere is denser than Earth atmosphere, which increases resistance to motion. When these two effects are combined, lower gravity and higher atmospheric density, the result is a regime in which falling motion is significantly slowed. Consider a droplet forming in a cloud. On Earth, gravity accelerates it downward, while air resistance increases with velocity until a steady falling speed is reached. On Titan, the same process occurs, but with different parameter values. Lower gravity reduces acceleration, while higher atmospheric density increases resistance. The consequence is that droplets can grow larger before falling, and descend more slowly once they do. Again, nothing in this description requires new physics. It is the same set of relationships, evaluated under different conditions. At this point, we can state the central idea of this opening section with precision. Titan is not a violation of our understanding. It is a confirmation of it. The same equations that describe Earth atmosphere, fluid flow, and phase transitions also describe Titan. What changes are the inputs? Temperature, composition, gravity, and these changes are sufficient to produce a world that appears familiar in structure, but is fundamentally incompatible in substance. This is the source of the tension Titan introduces. It is not that the world is chaotic or beyond analysis. It is that it aligns with our expectations at one level, geometric structure, while diverging at another, material composition. And because human intuition is tuned to recognize patterns rather than evaluate parameters, we are inclined to overestimate our understanding when confronted with familiar shapes. Therefore, as we proceed, our task is not to describe Titan in terms of how unusual it appears. Those are not useful categories in physics. Our task is to reconstruct it systematically from first principles, given a set of universal equations, and given a specific set of boundary conditions: low temperature, methane, rich chemistry, reduced gravity. What solutions emerge? And more importantly, what does this tell us about the range of possible worlds that can exist under the same physical laws? If in the first step we agreed on a discipline, that structure alone is not sufficient, then now we must proceed with something more precise. We must identify the equations that both Earth and Titan obey, because only when the mathematical framework is fixed can we understand how changing conditions produces a different world. We begin with something fundamental: the way an atmosphere holds itself in place. Imagine a column of gas extending upward. At every level there is a balance. The weight of the gas above presses downward, while pressure from below supports it. This balance can be described in a simple way. As we move upward, pressure must decrease, because there is less weight above. And the rate at which pressure changes depends on two things: how dense the gas is, and how strong gravity is. On Earth, this gives us a familiar atmosphere. Pressure drops gradually with altitude. But on Titan, something interesting happens. Gravity is weaker, but the atmosphere is denser. So instead of a thin, rapidly decreasing structure, we obtain a thick, extended atmosphere. Not because the equation is different, but because the balance between density and gravity has shifted. Now we move to the next relationship, one that connects pressure, volume, and temperature. In any gas system, if we compress the gas, pressure rises. If we heat it, particles move faster and pressure increases again. This relationship is universal, but what matters is the temperature scale. On Earth, typical surface temperatures allow water to exist in three phases: solid, liquid, and gas. But on Titan, at around 94 Kelvin, the situation is completely different. Water is no longer a liquid. It is locked into a rigid solid state, while methane, which is a gas on Earth, now occupies the role that water plays here. This brings us to a deeper principle: phase transitions. A substance changes from liquid to gas, not arbitrarily, but when thermal energy overcomes intermolecular attraction. If temperature is high enough, molecules separate. If it is low enough, they remain bound. So on Earth, water molecules have the right balance. They can move freely as a liquid, evaporate into vapor, and condense again. But on Titan, thermal energy is too low for water to do this. Instead, methane becomes the active fluid. Now we can reconstruct something important. The existence of a cycle requires only 3 ingredients: a liquid that can evaporate, an atmosphere that can transport vapor, and conditions that allow condensation. Earth satisfies this with water. Titan satisfies it with methane. And this is why both worlds display rivers, clouds, and rain. Not because they share the same substance, but because they satisfy the same physical conditions for cyclic behavior. We now turn to energy at a more microscopic level. Every molecule in a gas has kinetic energy, and that energy depends on temperature. Higher temperature means faster motion. Lower temperature means slower motion. On Titan, with temperatures near 94 Kelvin, molecular motion is significantly reduced. This has 2 consequences. First, chemical reactions occur more slowly because molecules collide less energetically. Second, liquids behave differently. Viscosity increases, and flow becomes more resistant. This means that even when Titan forms rivers, their dynamics are not identical to Earth rivers. The equations describing flow remain the same, but the coefficients inside those equations, density, viscosity, surface tension, all take on different values. Now, let us combine this with gravity. Motion under gravity depends on acceleration and on resistance from the medium. On Titan, gravity is weak, but the atmosphere is dense. So any object moving through it experiences strong resistance relative to its weight. The consequence is subtle but important. Falling motion becomes slow. Suspended motion becomes easier. Droplets can remain in the air longer. Clouds can persist. And transport processes occur over longer timescales. If we step back, we can now see the pattern emerging. Every major feature of Titan, atmosphere, weather, surface flow, can be derived from a small set of principles: balance of forces, conservation of energy, and phase transitions. Nothing in this list is unique to Titan. These are the same principles that govern Earth. And this leads us to the key conclusion of this act. Titan is not a different kind of physics. It is a different solution to the same equations. The difference arises not from new laws, but from new conditions. Lower temperature, different chemistry, weaker gravity. And once these parameters shift, the outcome shifts with them. So when we say Titan evolved like Earth, we must interpret that statement carefully. It does not mean the same materials or the same biology. It means something more fundamental. Both worlds follow the same mathematical framework, but explore different regions of possibility within it. And that realization changes the question entirely. Because now we are no longer asking why Titan is strange. We are asking, how many other worlds could exist, built from the same equations, but with parameters we have not yet imagined. Now that we have established the shared framework, the same equations, the same physical laws, we can move to the point where the divergence becomes unavoidable. Not because new physics appears, but because small changes in parameters begin to propagate through the system and amplify into completely different outcomes. Let us begin with motion under gravity. On any world, an object accelerates downward due to gravitational force. The strength of that acceleration determines how quickly velocity increases. On Earth, this produces familiar behavior. Objects fall rapidly, droplets fragment, and rain reaches the ground at a characteristic speed. On Titan, gravity is much weaker, approximately 1/7 of Earth, which means that for the same droplet, the downward acceleration is significantly reduced. But motion is not determined by gravity alone, because every moving object in an atmosphere experiences resistance. Resistance depends on the density of the medium, the size of the object, and its velocity. As velocity increases, resistance increases until it balances the downward force. At that point, acceleration ceases and motion continues at a constant speed. On Titan, the atmosphere is dense, significantly denser than Earth. So resistance becomes important very quickly. Combine this with weaker gravity, and the result is a system where terminal velocity is much lower. This leads to a direct consequence. Droplets of methane rain do not behave like water droplets on Earth. They fall slowly, remain suspended longer, and can grow larger before breaking apart. To understand why size matters, consider the balance between forces. The weight of a droplet increases with its volume, while resistance depends on its cross-sectional area. Volume grows faster than area. So larger droplets experience proportionally more downward force. But on Titan, because gravity is weak, this advantage is reduced, allowing droplets to reach sizes that would be unstable on Earth. Now we shift to energy at the molecular scale. Every physical process, whether evaporation, diffusion, or chemical reaction, depends on the kinetic energy of molecules. And that energy is determined by temperature. On Titan, with temperatures near 94 Kelvin, molecular motion is significantly reduced. Collisions occur with less energy, and many reactions that proceed easily on Earth become suppressed. This has a profound implication. Chemistry does not stop, but shifts into a different regime. Reactions that require high energy become rare, while low energy pathways dominate. Now consider the methane cycle again. Evaporation requires molecules to escape from the liquid phase, which depends on their energy. At low temperature, fewer molecules have sufficient energy to escape. So evaporation is slower. Condensation, however, becomes more efficient. Because once molecules lose energy, they remain bound more easily. The result is a cycle that remains active, but operates on longer timescales. Slower evaporation, slower precipitation, but still governed by the same thermodynamic balance. Now we introduce fluid behavior. When a liquid flows, its motion depends on viscosity, density, and external forces. Viscosity represents internal resistance. how strongly molecules resist moving past each other. At low temperatures, viscosity increases. Because molecular motion is reduced, so methane rivers on Titan, while still flowing, do so under different conditions than water rivers on Earth. Combine this with lower gravity, and you obtain slower currents, different erosion patterns, and altered sediment transport. Yet the shapes that emerge, channels branching, networks, basins, remain consistent with the same governing equations of fluid flow. This is the critical point. Geometry is preserved because the equations are preserved. But the dynamics differ because the parameters differ. Now we extend this reasoning to surface materials on Earth. Rock is solid because temperature allows atomic bonds to remain fixed. Water ice melts under normal conditions, and therefore behaves as a liquid. On Titan, the temperature is so low that water ice does not melt. It behaves as a rigid solid, effectively playing the role of rock. This inversion is essential. Materials exchange roles not because their intrinsic properties change, but because environmental conditions shift the phase in which they exist. At the same time, hydrocarbons in the atmosphere undergo complex reactions, forming solid particles that settle on the surface. These particles accumulate and can be transported by wind, forming dunes. Again, the mechanism is familiar. Wind carries particles. Particles accumulate into patterns. Dunes emerge. But the material is different. Not silicate sand, but organic compounds. If we pause here, we can see the pattern repeating across every scale. Droplets, rivers, landscapes. The equations remain unchanged, but the inputs alter the outputs. And this leads to a deeper realization. When we say Titan is Earth-like, we are describing a similarity in mathematical structure, not in physical substance. The world is not imitating Earth. It is solving the same equations under different constraints. And when you follow those equations carefully, without relying on intuition, the result is not confusion, but clarity. Titan is not strange because it breaks the rules. It is strange because it follows them exactly, but in a region of parameter space where our everyday experience no longer applies. If we now step beyond local processes, beyond droplets, clouds, and rivers, we arrive at a broader question. What does Titan represent? Not as an isolated object, but as a solution within the space of all possible worlds. Because once we accept that the same equations apply everywhere, every planet, every moon becomes a test case, a realization of those equations under a different set of constraints. Titan is not simply another moon of Saturn. It is a system in which atmospheric physics, chemistry, and surface processes have reached a stable configuration, under conditions that differ from Earth in three essential parameters: energy input, temperature, and composition. Let us consider energy first. The Sun provides the dominant external source, but at Titan distance, that input is weak. This means that any process requiring significant energy, whether it is rapid chemical reaction, strong convection, or high-temperature phase transitions, is suppressed. Instead, the system evolves towards slower dynamics. Energy is still transferred, but over longer timescales. Gradients persist longer, and equilibrium is approached more gradually. Now, consider temperature. At around 94 Kelvin, the entire hierarchy of material behavior is reorganized. Water becomes structurally rigid. Hydrocarbons become active fluids. And chemical pathways shift toward those that require minimal energy input. Composition then determines what is possible within this temperature regime. Nitrogen provides the bulk of the atmosphere. Methane introduces volatility, and complex hydrocarbons emerge through photochemical processes. Together, these components define the range of reactions, the stability of phases, and the structure of the surface. When we combine these three parameters, a coherent picture emerges. Titan is not a partial Earth. It is a complete system. Internally consistent, governed by the same principles, but occupying a different region of possibility. This allows us to interpret Titan in a new way, not as a failed version of Earth, but as an alternative outcome. If we begin with the same physical laws and vary only initial conditions, we do not obtain small deviations. We obtain entirely different worlds. Now we extend this reasoning further. Beneath Titan's surface, evidence suggests the possibility of a subsurface ocean, not of methane, but of liquid water mixed with other compounds. This introduces a layered structure, a cold hydrocarbon surface, above a potentially warmer interior region, where pressure and internal heating allow water to remain liquid. If this is correct, then Titan contains two distinct chemical environments, one dominated by hydrocarbons at low temperature, another dominated by water under higher pressure. Each of these environments follows the same thermodynamic rules, but the available reactions differ. And this leads us to a question that extends beyond planetary science. What are the necessary conditions for life? On Earth, life is based on water, complex carbon chemistry, and a continuous flow of energy. But these are not assumptions built into physics. They are outcomes of specific conditions. On Titan, the situation is different. Temperature is low, energy is limited, and the dominant liquid is methane. From a thermodynamic perspective, any system that maintains structure must balance energy and entropy. If energy input is too low, complex organization becomes difficult to sustain. This suggests that if life were to exist on Titan, it would not resemble terrestrial life. It would operate more slowly, rely on different chemical pathways, and exist near the limits of what thermodynamics allows. Some theoretical models propose structures based on hydrocarbon membranes, capable of maintaining boundaries in liquid methane. These are not speculative in the sense of violating physics, but they remain unconfirmed. What matters for us is not whether life exists there, but what Titan reveals about possibility. It shows that Earth is not a universal template. It is one realization among many, and that life as we know it is not guaranteed by the laws of physics, but by a narrow set of conditions within those laws. When we extend this to the scale of the universe, the implication becomes clear. If the same equations apply everywhere, then variation in initial conditions will produce a vast diversity of worlds. Some similar to Earth, many fundamentally different, Titan is one such example. Not extreme enough to be dismissed, not similar enough to be familiar, but positioned in a region that forces us to refine our definitions. It teaches us that resemblance at the level of structure does not imply equivalence at the level of substance, and that understanding a world requires more than observation. It requires reconstruction from first principles. And once we accept this, the question changes again. Not what Titan is, but how many other configurations exist, waiting to be realized by the same equations, under different conditions. If we have followed the argument carefully, step by step, without skipping over the equations, then by now something should feel different. Not about Titan itself, but about the way we interpret worlds. Because what began as a question about a distant moon has become a question about the nature of physical reality. We started with a simple observation. Titan looks familiar. It has rivers, lakes, clouds, and weather. And if we had stopped there, we would have concluded that it is a variation of Earth. But we did not stop there. We asked what those structures are made of, what equations govern them, and what parameters define their behavior. And once we did that, the conclusion changed completely. Titan is not a version of Earth. It is a different solution to the same mathematical framework. This distinction is not philosophical. It is technical. Because in physics, an equation does not describe a single outcome. It describes a family of possible outcomes. And what selects one outcome over another are the conditions under which the equation is applied. Temperature, pressure, composition, and gravity are not secondary details. They are the inputs that determine which solution becomes real. On Earth, those inputs produce a world dominated by liquid water, rapid chemical reactions, and a biosphere that evolves on relatively short timescales. On Titan, the same equations operate. But the inputs shift. Temperature drops. Energy becomes scarce. Methane replaces water as the active fluid. And the result is a system that mirrors Earth in structure, but diverges completely in substance. Now we must take one final step. And it is not a step outward, but a step backward. Back to the assumption we made at the beginning, that familiarity implies understanding. Titan shows us that this assumption is unreliable, because the mind recognizes patterns, but physics requires parameters, and the two are not the same. A river is not defined by how it looks. It is defined by equations of flow. A cloud is not defined by its shape, but by thermodynamic balance. And a world is not defined by its appearance, but by the values that enter its governing laws. Once we accept this, something important happens. We stop asking whether another world is like Earth, and we begin asking a more precise question. What set of parameters defines this world, and what solutions emerge from them? This shift in perspective is subtle, but it is essential, because it removes us from intuition and places us inside the logic of physics itself. Now consider what this implies at a larger scale. If the same equations apply everywhere in the universe, then every planet, every moon, every system is simply another realization of those equations, under different initial and boundary conditions. This means that Earth is not central. It is not the default. It is not the reference from which all other worlds deviate. It is one point in a vast space of possibilities. Titan occupies another point in that space, not extreme enough to be dismissed, not similar enough to be familiar, but positioned in a region that forces us to refine our definitions. And this is why Titan feels disturbing. Not because it is chaotic, not because it is unknowable, but because it is understandable in a way that contradicts our intuition. It follows the rules exactly. And yet the result is a world where everything familiar has been reassigned. Water becomes rock. Methane becomes liquid. Rain falls slowly. Rivers flow under different conditions. Chemistry proceeds at a different pace. Nothing is violated. Everything is consistent. And that consistency is precisely what forces us to reconsider our assumptions. Now we return to the deeper question. Not whether Titan hosts life, but whether life itself is tied to a specific set of conditions, or whether it is a more general consequence of physical law. On Earth, life depends on liquid water, on a continuous flow of energy, and on chemical pathways that operate efficiently at moderate temperatures. On Titan, those conditions are altered. Temperature is low, energy is limited, and the dominant chemistry is different. From a thermodynamic perspective, this places strong constraints on complexity, because maintaining structure requires energy flow. And if that flow is weak, the system evolves slowly. This does not make life impossible, but it changes what life would mean. It would not resemble the systems we observe on Earth. It would operate on different timescales and rely on different mechanisms. Whether such systems exist, we do not yet know. But the important point is that physics does not forbid them. It only constrains them. And this is perhaps the most important lesson Titan offers. Physics does not determine outcomes directly. It defines the space of possible outcomes. Within that space, different worlds emerge. Some familiar, some not, but all governed by the same underlying structure. So when we look back at Titan, we should not see it as an anomaly, but as a demonstration that the universe is not built from isolated rules, but from a unified framework capable of producing a vast range of realities. And in that sense, Titan is not distant. It is not separate. It is connected to us through the same equations that govern our own existence. The difference is not in the laws, but in the conditions. And once we understand that, the question changes one final time. Not what Titan is, but how many other worlds exist, waiting within the same mathematical structure, to take on forms we have not yet imagined. As Richard Feynman once expressed in his own way, nature does not adjust itself to our expectations. It reveals itself only through the consistency of its laws. And our task is not to simplify that reality, but to understand it as it is. Thank you for staying with this journey, not as passive observers, but as participants in the process of understanding.